right, as a heads up, I did just publish the new module that has the slide deck and everything that you need for today. So that's now available to you. Sorry about that. You gonna participate today? Okay, so now this should, yes, we're seeing this. This is now available to you. People are seeing the slides. Yes, thank you for the thumbs up. Okay, so that's there. I've also put the exam 4 helpful information. We're on to our last chunk of content for exam 4, and then of course we'll do a little bit more content that's going to be on the final, so that was a lie. But we're really actually getting close to the end of the semester, which is wild. We have this week, a week from today is Veterans Day, so we don't have class that day. And then we'll have lecture, and then another lecture, and then review, and then midterm 4, I think. That's how the structure is going to go. So there's not, good news is there's not that many lectures between now and midterm 4. So take that as you will. Okay, we are going to totally shift, well, we're not totally shifting gears. We are now going to actually dig into the conceptual reasonings for why K is K. So we have been looking at so many different Ks, all right? We've talked about KC, KP, KA, KB, KSP, and KF, okay? And we have just accepted that those values are the values that they are, right? And we use them to make sort of some statements or some, I don't know, guesses or hypotheses about how a reaction will proceed. So we could say we know what K is, so that we know that at the equilibrium, that's the balance of products and reactants that the system wants, that they will spontaneously move to achieve, okay? One of the first things we do, what does spontaneous mean? Okay, so we're going to start there on the side. But this feels like kind of coming in and out, which is not great. The system just, so like we don't have to do anything. The system will go there on its own, okay? And now the question is why that value of K? If it is K equals 1, where we have 50-50 of reactants and products, what is the thing that dictates that that's the place where the system is happy? That's what we do in chapter 19. So this is the why. So first we're going to start by that definition, that word spontaneous, and what does that mean? Okay. So a spontaneous process, your book uses this physical process for us, where if I have an egg and I'm holding it here and I let it go, it will spontaneously fall, right? All I have to do is just like let it go, and it occurs without any more assistance. So a spontaneous process occurs on its own without assistance. Okay, that's what we mean by spontaneous. And on the next slide, we'll do it for like an actual reaction, so we can get to something that we have been talking about. But in this case, I dropped it looks like I've wasted 2 eggs in this example and dropped them both. Non-spontaneous, actually I'm going to say the reverse of a spontaneous process is non-spontaneous. Right, those eggs aren't going to pick themselves back up. I could wait for billions and billions of years, and those eggs are never going to pick themselves back up, reform, and come back up. They will just get moldy there. So, but we do want to make just a little caveat, like a nuance here. When I say non-spontaneous, I don't mean impossible. It's not impossible. We just need outside assistance, aka like work needs to be done. Okay, so just to clarify here, it's not that I can't make a non-spontaneous process happen, it's just that it needs me to do something, or that the world has to do something for it. Okay, so let's instead of looking at eggs falling, let's look at a spontaneous process when we set up a reaction, okay, something that we're familiar with. We're going to look at A turns into B, all right, with a K equal to 1. So that's what we're going to set up on the next slide. All right, so here's my reaction. Maybe reaction equilibrium arrows would have been better here. Okay, but K equals 1. So I know that at equilibrium I should have equal amounts of A and B. So I'm going to draw this curve, sort of this visual, right? So over here I have 100% A. Over here I have 100% B. At the middle here I have 50-50. Okay, that is where K is. K is equal to 1. All right, so if I start, I'm going to make that curve hit. All right, so if I start with 100% A, I know the system will spontaneously make B. Right? If I started over here, if I had 100% B, the system will spontaneously make A. That's where the system wants to be. We'll do it until we have 50-50. If I were down at the bottom, when I am at equilibrium, down at the bottom here, both directions would be non-spontaneous. If I am already at equilibrium, the system will not spontaneously make more A or make more B, right? It's non-spontaneous in both directions here. It's already happy. Okay, we can connect this to some of the other technology that we had here. So over on this side here, Q is less than K. Over on the right side here, Q was greater than K, and here Q is equal to K. Okay. All right, and so again, it's not that I could never make some of this A turn into B or vice versa. It's just that I would have to intervene. I would need to go do some work. Okay, the system would not do that on its own, even if I did it for millions and millions of years. Okay, so I want to especially highlight this concept of spontaneity, and then also what would be non-spontaneous, right? If you're already at equilibrium, neither direction is spontaneous. You're going uphill in both directions. Okay, so now that we have spontaneous and non-spontaneous defined, I want you to think about these two processes. Okay, we're going to lean on some of your intuition, your knowledge of the world already. We're at room temperature and pressure, and I have a block of ice out on the table. Does the block of ice spontaneously melt? Yes. We know that if I put ice out here, it is going to melt into liquid water, right? That is a spontaneous process at room temperature. And so you guys already know this one. This is spontaneous. With the caveat, at room temperature, okay? So that's just a little like foreshadowing here. Temperature is going to matter when we think about is something spontaneous or not spontaneous. Yeah. Sorry, say it again.
So even if it needs to use heat energy to perform a process, that still makes it spontaneous.
Are you looking at one of these processes particularly? Oh, like for this one here? Yes. That's half the equation.
Because then also like if you think about like solubility and how like it'll create the solid but then also heat you, does that not make it like
You are looking at half of the process, half of the equation right now. We are going to introduce the other half. And then we will talk about how those two combine to give us what I will call the oracle of spontaneity. Yes. I like where your head is at, okay? How about this one? When I remove that partition, do these spontaneously mix? Yes. They're not gonna self-select into either side. This is also spontaneous. All right, so the question is, and I think what you were getting at, Dylan, was that what is it about these two things that make this spontaneous? Okay, what is the oracle? So when I get to equations like these, or these processes, these chemical processes that we might not be as familiar with, that I couldn't ask you on an exam, is this spontaneous or not? How would you assess these? How would you look at them and say, I know that it is or isn't spontaneous? We need some metric to do that. So it turns out all of these are spontaneous processes, so the combustion of gasoline, the oxidation of sugars, the formation of water, all of these are spontaneous. And you might notice that all of them are exothermic. Okay? So this was the first hypothesis on spontaneity, was that if you were an exothermic process, it would be spontaneous. Okay? That was like so cruelly. Berthelot's suggestion for spontaneity was that, hey, is it exothermic? Then that would be a spontaneous process. If it was endothermic, then that would not be a spontaneous process. However, this was very easily debunked, right? All we need is one endothermic process that is spontaneous. And we already looked at one, okay? So this is not always true. Endothermic, okay? And we just looked at it on the last slide, okay? So actually 2 slides ago. So let's look at that again, all right? When we already said you knew this to be true, I have a block of ice. And if it was at 298 Kelvin, sitting out here at room temperature, it will spontaneously melt. This is an endothermic process. That water, okay, in the solid form, needed to absorb energy to break up all of those crystalline water interactions to make the liquid form. Okay, that's this part of our graph right here. We needed to absorb energy, so this was an endothermic process. That was spontaneous. Okay, so it can't just be the enthalpy change that dictates whether or not something is spontaneous. There's something else at play here. Okay, so we know that we have to add energy. In other words, our delta H, what I might call delta H of fusion. So my enthalpy of fusion is positive, right? So in other words, it's an endothermic process. We're breaking interactions. So when it is at this temperature, that's spontaneous. Okay, so it's very easy to break down that idea that exothermic is the metric, is the oracle, is the thing that dictates whether or not it's spontaneous. That's not true. Here's an endothermic process that is spontaneous. So what is it that dictates spontaneity? That's what we're trying to figure out here. So we're going to do a little thought experiment here. Okay? Here's just what I said, like this was wrong. It was very easy to break that down. Again, what is the thing? We need a quantitative measure of a process to tell us, is it spontaneous or not? And it's not enthalpy, it's something else. Although it is going to, not that we're going to shun enthalpy. All right, so I'm going to now, instead of putting my block of ice out, I have put my cup of coffee out. It is hot. Okay? Think to yourself, does that cup of coffee get colder as it sits out in this room, or does it get hotter? Again, you all already know the answer to this, right? It would be insane of me to say that this coffee is going to get hotter as it sits in this room, right? We all agree that doesn't feel comfy, right? As this sits here, heat leaves. This is a truth of the universe that we should acknowledge here. Heat always moves from hot objects to to cold objects. Okay? That is true. Another way of looking at this, in my cup of coffee, I could look at that. I have concentrated thermal energy. And what happens spontaneously is that it dissipates. Okay? It disperses. Okay? So the heat disperses. Okay? It is never going to condense. Right? We are never going to spontaneously condense energy. It spontaneously disperses. Maybe another way of writing this is that, what did I write here? Energy spontaneously moves from high concentrations to low concentrations. Okay? I am not going to take the heat, the energy, the thermal energy from this room and put it into one spot. I can't, that's not going to happen spontaneously. It goes the other direction. Okay, so it's something about this dispersion or spreading out of energy, that's the thing that drives spontaneity. And we need another thermodynamic quantity for that. Okay, and that's what we're going to describe with entropy, which is capital S. Okay? So here I've defined it as a measure of the tendency for energy to spread or disperse, which also means that we're reducing its ability to accomplish work. Okay, so a couple things about entropy. Entropy is a state function rather than a path function. Just as a reminder, we tend to capitalize state function variables. Okay, and these are usually in lowercase, just as a point on notation. Okay, importantly, though, what this means for us is that if we want to look at the change in entropy, we don't care about the path that it took to get there. We just need to know the final entropy and the initial entropy. Okay, so I can write this. That's the being a state function allows me to write delta S equals S final, entropy at the final conditions minus the entropy of the initial conditions. Okay. I'm going to define it as, for a specific instance, if we are in an isothermal process, in other words, we're not changing the temperature. So for an isothermal process, so T is constant, then I can write delta, and we're going to think about delta S of the system here. So if we are thinking about my coffee cup here, my coffee cup and my coffee inside of it, that was my system. Everything around it was the surroundings. I'm going to define delta S of the system as the heat of the reversible process, which we're going to come back to that in a second, divided by the temperature. So this is heat transferred if reversible. Which means that my entropy units are going to be joules per Kelvin. That's what we're going to work in for entropy. So units are joules per Kelvin. Okay, and I'm going to write this equation out. We are going to use later on in an example problem. I want to just say one more thing about that. So if I want to put that statement into a sentence, say delta S of the system is equal to the heat transferred process were reversible. Actually, heat transferred in a reversible process. And again, we're going to define reversibility and irreversibility in the next couple slides. So just put a pin in that for now. In a reversible process, divided by T. Okay, so again, temperature is very important. So if we're thinking about the direction of transfer, like where is this energy going, it's important to know how hot it is. What is the temperature where that heat is heading to or where it is leaving from? Okay. We're racking up some definitions here, which is like this first part of the chapter is very definition heavy where I feel like I just yell at you a lot and you memorize these things or you get comfortable with them, and then we'll get into some process-based stuff towards the end of today. All right, so what is this reversible process jargon? And you might have noticed, hey, how did I define a state function based on a path function? Okay? And the thing is that reversible path that I'm talking about is unique. There is only one reversible path. Okay? So that's what we're going to talk about and define in the next 3 slides. So a reversible process, okay, occurs in such a way that the system and surroundings, so like the whole world, the whole universe, can be restored to the original states by exactly reversing the process. Okay, so if something happens and then I reverse it and everything in the world is exactly the same, all the energy is in the same place as it was before, that's a reversible process. An irreversible process is where that's not true. Okay? So a change occurs in such a way that the system and surroundings, so again, like the whole universe, cannot be restored to the original states. By exactly reversing the process. So a state function, good question. Okay, I'll come back to that in just a second. Just so that people can get this down, and then we'll go back 1 slide. How would you have intuited that? You wouldn't have. I don't know if I have a good answer for that question. I can't put myself back into that person's mind of like, why would we take these 2 things? Okay, so we're going to step back just a little bit for this state function versus a path function. So there's my favorite example for state versus path function. If you are climbing a mountain, okay, and this is your base camp down here, okay, and then you're climbing up to the top of Mount Everest. Okay, so my altitude change, okay, if I go from here to here, altitude is a state function. Or my change in altitude is a state function. Okay? Like it doesn't matter how I got from my base camp up to the top, my change in altitude is always the same, right? The way I got there is a path function, or the distance that I traveled. So like distance traveled is a path function. Okay, so going from here, like maybe there was like a really steep set of stairs that I could walk, and I took that route. That would be different than if I took like the logging route that was not as steep and went all the way around. To travel, I would have to walk a lot farther doing that, but my altitude change was the same. Okay, so that's a path function. It matters how I got there. The number of steps I took will matter if I went up those stairs or if I went around and around and around. But in both cases, my altitude change was the same. So altitude would be considered a state function, and my path, my distance traveled, would be a path function. Say the room would, the room would get hotter, but we couldn't measure it. Like this room is too large to notice that change in temperature. But yes, that heat had to go somewhere. It's making the molecules move faster in this room. It went somewhere, but we just wouldn't have noticed a temperature change because my small cup of coffee is too small to impact like the temperature of this room. Okay. All right. So I'm guessing reversible and irreversible right now is just like, sure, you yelled some definitions at us. Let us look at two processes. All right, so we are going to go back to our piston, which is like, I don't know, thermodynamics' favorite system. And I'm going to take compressed gas. So I've got my piston. I put a gold weight on it, okay, and I compress my gas. Above it, I have a vacuum. There is nothing above it. All right, so when I remove that weight, there is nothing holding that gas back from expanding. So it does. It expands spontaneously. The system doesn't have to do any work. It is not pushing against anything. There's no molecules up in this headspace here to work against. This happens spontaneously. So this is a spontaneous process. This step right here, okay, when I remove the weight. That gas expands, okay? And the system did no work. All right? However, what if I decided, hey, I actually would like to have that compressed again? I cannot, that will not happen without me doing work or the world doing work on the system. Okay, so now work must be done to compress the gas. Work was done. In other words, now the universe, the surroundings have done work on the system. We are not back at our original state. This was not a reversible process. This was irreversible. Because these two are not the same, right? In one direction, no work was done, and in the other direction, to try and get back to that same spot, work needed to be done. So now, yes, we are back at the same physical position, but energy has had to be distributed in a different way. We're moving it around. All right, so that's irreversible. Okay, now the question is, can we make an irreversible process reversible? And the answer is, hypothetically, yes, we can. All right, so here, instead of a weight, like a full mass sitting on top of that piston, I have a pile of sand. Okay, and so instead of brushing the whole pile off at once, okay, like I had removed the weight, I'm going to take one grain of sand off at a time. In other words, I'm going to make infinitesimally small changes. I literally looked up how to spell infinitesimally before class. Infinitesimally. Small changes. When I do it this way, the system never leaves equilibrium because I have made such an incredibly small change. And so no work is ever done in either direction. And so I can return it. I can actually actually get it back down. Small. All right. But in this process, I could then start adding it back on. Over here, when I pull this off, this thing shoots up. Maybe I lose some heat in the friction there. It's out of equilibrium. It's like has to like figure out exactly where it wants to land. And over here, I'm going very slowly and carefully and moving this thing so tinily that I've never actually moved off of equilibrium. And again, that's hypothetical, okay? This is a reversible process. I can make an irreversible process reversible with these infinitesimally small changes. But of course, that's hypothetical. So we can come to the conclusion that all real processes are irreversible. But it is useful to have this concept of reversibility because that's the path that we're going to talk about when we define entropy. That was my Q reversible, Q rev as I wrote it. Okay? So we can approximate, but we can't make it perfectly reversible. No, we would like to attain reversibility, but we can only approximate it. Okay? So I have another way of thinking about this, another analogy. Okay? So this one, box that one will be good. Like this should be one that you have. Okay? That definition. All real processes are irreversible. Okay? So now I'm going to do a sledding analogy. All right? You're at a hill. And you are at the top of the hill. Maybe you walked up on this side of the sledding park. All right, there I am. Okay. When I go down, okay, as soon as I'm inching forward, as soon as I let go, that is a spontaneous process, right? I will find myself at the bottom of the hill here. All right, however, if I would like to go, if I want to go sledding again, I now need to get up and I need to walk up the hill. When I get back to the top of the hill, am I the same as I was when I first started this? No. I'm tired. I just had to put in a lot of work. I had to climb back up that hill, probably like slipping and falling and avoiding little kids as they came down, right? So I am not the same. I can walk back up, but I had to do work. And now when I get back up to the top, I am not the same. So this was not reversible, it was irreversible, because to go back up, the energy in the world is different, right? I had to use some molecular energy in me to like huff and puff up the hill. I'm sweating, I'm hot now, that's dissipating out into the world. So the exact conditions are not the same. Even though I got back up to the hill, the world is not exactly the same, okay? So going back this way is non-spontaneous. And this was irreversible. Spontaneous processes, by definition, are also irreversible. So a spontaneous process is irreversible. If I wanted to then say, how could I make this sledding hill a reversible process? What would that look like? That would be me taking this hill, okay? It wouldn't be a very fun sledding hill anymore, but I could stretch it out infinitesimally long, right? Or I get infinitely long. We're not making it small. My steps would be infinitesimally small. If I were to take this sledding hill and make it like this, and that again, this is a hypothetical concept because I cannot stretch it out and still actually think about making it all the way up. But at this point, yeah, I could go down and I could go back up because all these steps are so incredibly tiny, I never have to do any work, Okay, so this might be really long. I just, oh no, it's still there. Reversible, but again, hypothetical. Not only would this be an incredibly boring hill to sled on, it's also not real, right? So I don't need it, there's no steps up to take because they're infinitesimally small. No steps up to take, they're so incredibly small. Okay, so again, this is the hypothetical concept. But it is a specific path that I can think about, right? And that's where we're going to use our definition when we come back to calculate delta S for the system. So we now have those two. So we're gonna go on to do some calculations here, and we are again reminding ourselves that we are heading towards what is the thing that tells us if something is spontaneous or not. That is our goal. All right. So we're going to approximate a reversible process. Okay, again, but now we're going to do it with our brick of ice that I've set out here. I have 18 grams of ice sitting out on this table here, but in this scenario, I have turned the temperature down in the classroom. We are now all sitting at 273 Kelvin plus a teeny tiny amount. Okay, so we're all cold and miserable. Okay, and I'm going to calculate some of the delta S of our system, so the change in entropy for our ice, the change in entropy for the surroundings, like all of us, and then we'll calculate delta S of the universe. Okay, so I have 18 grams sitting, this by definition, if our ice is at 273 Kelvin, and the room is just a tiny hair higher in temperature. Okay. We are going to then, I'm going to switch to the next slide here because I've got all this information there as well. Oh, no, I'm just kidding. We're talking about this point right here. We're melting. Again, I need to know the energy, the heat that is required to make this happen. That is my delta H of fusion. We're going to assume that we're at constant pressure, which is a good assumption because we're doing this out in the open air, so we don't have to worry about any contributions from PV. All right. So we're going to jump now to this. We're going to calculate entropy change for the system, all right, which again is our brick of ice. We know that this is at 273 Kelvin. We're going to see how, what happens with it in terms of our entropy. So we're sort of like taking this heat and we're saying, okay, at certain temperatures, how, like that dispersal within this temperature. I guess that's it's like barely intuitive, but there's a little bit there. For this Q, reversible, I am going to take my enthalpy needed to make this happen. That is my enthalpy of fusion. So I have 1 mole. I said we had 18 grams. I did that so that we could just do 1 mole. So I have 1 mole. Okay? How much heat does that 1 mole of water, that ice water, need to absorb, okay, to actually melt? Okay, so that's 6,000 joules per mole. Okay, so I'm going to use this here, and then this goes here. All right, and I know this should be a positive number again because from the system's perspective, right, our ice needs to be absorbing that energy. It's got to absorb the energy to break up those interactions. So this should be positive. Write this in, so I've got 6.01 kilojoules per mole. I had 1 mole, and this system, okay, so importantly, my system is the ice. The system is at 273 Kelvin. Okay, I'm going to then switch over to joules because typically our delta S, any entropy calculations will be in joules, not kilojoules. So this gets me 22.01 joules per Kelvin. That was my change in entropy from going from solid ice to liquid ice. But remember, in the system, this is still 273 Kelvin. It's just now liquid instead of solid. All right, so we have our delta S of the system. Now I want to think about your question, which was like, what happens to the surroundings? Okay, so in theory, the room just got a teeny tiny bit colder. You might consider that because my ice had to absorb that energy from somewhere to melt. So from the this feels like up in the top. Is my voice changing at all to you guys? Does it sometimes sound like the mic is picking up and sometimes it's not? Okay. I will complain to facilities about that. I don't know why that's happening, but I will continue to project in my loudest. All right, so now I'm gonna say I know that the surroundings must have been where my 6,010 joules came from. So from the surroundings perspective, this is gonna be negative, right? The surrounding, so the ice melted here, right? And to do that, I must have put energy in. Heat had to go in to break up those interactions to make it melt. Where did that heat come from? It came from the surroundings. Okay, so I'm going to have negative Q rev here. It's just the opposite of where my system took in. Okay, that had to come from the surroundings. And from the surroundings perspective, it lost it. So this is going to feel, at this point, maybe a little trivial. Okay, and again, our surroundings are this 273 plus 1 over infinity. It is just a hair higher, just enough to make this melt. Okay, but for us, that means that my change in entropy of the surroundings were equal in magnitude but opposite in sign. Okay? So I know that heat had to come from somewhere. It came from the surroundings, so I gave it a negative sign. So if I want to calculate the entropy change for the universe, our universe is just the entropy of the system plus the entropy of the surroundings. And so in this case, since they're equal and opposite, our entropy change was 0. You're like, oh, wow, yay. That is typical. This is a definition and a characteristic of a reversible process. This is a truth. A reversible process will have a delta S of the universe equal to 0. Of course, it's unlikely that we'll do a reversible process. This is a hypothetical. So now I'm going to take us all out of our torture. I'm going to turn the room back up to 298 Kelvin, and we're going to recalculate our delta S of the universe at our normal human temperature that we'd want to be at. All right? So we're increasing the surroundings. Importantly, the surroundings are 298 Kelvin, but my ice is still ice, which must mean that it's still 273 Kelvin. It's still frozen. It just hasn't gotten that last little bit of energy needed to melt, okay? That delta H fusion. So now we're going to do this again, okay? So this is at 298 Kelvin. All right? You all already know that this is a spontaneous process. You've already said it. The ice is going to melt, okay? So what does that mean? What we want to know is, what does that mean for delta S of the universe? Spoiler, that's where we're heading. We're really curious about the sign of delta S of the universe, okay? That's where we're going with this whole conversation. Delta S of the system hasn't changed. It's still absorbing this 6,010 joules. And it is still a block of ice at 273 Kelvin. So its change in entropy was 22.01 joules per Kelvin. The entropy change in the surroundings is now what's different. Yes, it still contributed those 6,010 joules, right? It still gave that up. It was at a higher temperature. It was at 298. Okay? So I guess you might be able to interpret that or think about it as like, okay, same amount given, but it was at a higher temperature, so like it was less of a percentage of what was out in like this warmer room. Okay? So that now is negative 20.2 joules per Kelvin. And when I go to calculate my delta S of the universe, which is the sum of the system and surroundings, that gives me 22.01 minus 20.2, and that is 1.8 Kelvin. That is greater than 0. This is going to be our oracle, the thing that tells us if something is going to be spontaneous. We're asking ourselves, is delta S of the universe positive? Yes, then it is spontaneous. Okay, so delta S of the universe is greater than 0 for spontaneous processes. This is the thing. All right? I'm gonna hopefully like prove that to you, or at least like drive home. We're gonna ask ourselves, what would happen if we tried to make it negative? Okay, what if my change in entropy of the universe were negative? Could I have a spontaneous process that way? All right, so let's do that. We're running the same math again, but this time I'm now wondering, could I make this true? Could I make delta S of the universe a negative number? What would I need for that to be true? We're stuck with this. This delta S of the system has to be 6,010 joules per 273 Kelvin. Those two things can't change. So I know that this is going to be my 22.01 joules per Kelvin. That's got to be true. If I want to make this negative, I need to make my temperature of the surroundings colder. I need that number to be smaller, right? Just like mathematically, if I want to bring these two, the delta S of the surroundings and system together to make it negative, I need this to be a smaller number. All right, so then we would say we've got negative 6,010 joules per, and I just said, well, okay, I'll make it 200 Kelvin. That would give me negative 30.1 joules per Kelvin. And so now, when I add these two together, I do get a negative value for delta S of the universe. But we have a problem. Is this process spontaneous? Do you know, like, use your intuition. If I had turned the room down to 200 Kelvin, does that brick of ice melt? No, it's too cold in here. That ice is not going to melt at 200 Kelvin. It is too cold. It can't melt. So this is once we have a negative value for delta S of the universe, that means it's non-spontaneous. It will not happen. So when delta S of the universe, what we have to, the gymnastics we have to do to get to a place where it is less than 0 means that we've put us into a place that's not a spontaneous process. It's non-spontaneous now. So delta S of the universe, when it is less than 0, would mean non-spontaneous process. The only way to get to that being a negative value is putting us into a scenario that's not spontaneous. We know ice won't melt when it's colder than 0 degrees Celsius. Okay? So this is the thing we are going to check. All right? Delta S of the universe is the thing we want to know about. That is the second law of thermodynamics. Okay? So that's the piece of information we're going to be looking at throughout the rest of the chapter. We're going to say, does this thing happen? Is it spontaneous? We'll calculate delta S for the universe. We're going to call it something different, which I find annoying. We're going to actually call it Gibbs free energy, and we'll make a little bit of a change. But at the core of it, does delta S of the universe increase? If that's the case, it's spontaneous. Okay, so we're going to write delta S of the universe. If it's greater than 0, that's a spontaneous process. If it is less, it's not spontaneous. And if it were equal to 0, that would be an indicator that we have configured a reversible process. Again, that's hypothetical. Okay. I'm sorry it took so long to get here, but I finally have a practice problem for you so you can take a break from listening to me. I want you to calculate the entropy of the system, okay, for this ethanol that is condensing. So read through that. Maybe like have a little chat with somebody next to you. I know that was a lot of like pretty dense information. So take a couple minutes. All right. If you have gotten to an answer, show me 1, 2, 3, or 4. If you haven't gotten there, you can like give me a 0 of like, not landing. Good, good. I'm seeing lots of correct answers. Let's look at this together. For these questions, it is very likely that you are going to see some phase change questions on your exam. I always recommend draw out what is happening. Ethanol gas condenses to liquid, okay? We are thinking about, like, I have a vapor cloud of ethanol. Okay, so here's my ethanol, and it's in the gas phase. And I'm thinking about it condensing to a little bit of liquid, right? So is that endothermic or is that exothermic? Okay, I am making interactions. Those ethanol molecules are coming together, which drops their energy. They come together because it lowers their potential energy because they're forming some really nice intermolecular forces. They get to form hydrogen bonds. So this is an exothermic process. From the perspective of the system then, the system is releasing energy. It's exothermic. We define that as negative. So I know right off the bat that it should be one of my negative numbers. I tell you that the molar enthalpy of vaporization is 38.56, but I'm not talking about vaporizing. That would be liquid to gas, right? I'm going the other direction. So it's just the negative value of that. Does that make sense? So again, this is why I think it's useful. This process would be negative 38.56 kilojoules per mole. That 38.56 would be if I had a mole of liquid of ethanol and I pull it out into the gas phase. This is vaporization. But per the question, I have the gas and I'm going to the liquid. So I'm doing this top process, not this process. Okay, and this is 30. I'd have to put in 38.56 kilojoules per mole to do that. And since I'm thinking from the system's perspective, I should have a negative number. Give me like a thumb meter in that explanation. Does that feel good-ish? Okay, so again, I think it is useful. I gave you guys a question like this on your post-lecture questions. It is useful to write out what is the process that you're looking at, and then ask yourself, what's that number at, like, what's the number giving you? That's giving you vaporization. We're talking condensation process. Okay, so delta S of the system, I have 1.5 moles of my ethanol, and I'm going to multiply it by negative 38.56 kilojoules per mole. That's going to tell me how much energy was going to be released as this thing condenses. Okay, and then I'm going to divide it. We're not going to forget to divide by temperature, and we're not going to forget to put it into Kelvin. So 78.3 degrees Celsius plus 273. And so that gave me that negative 1, and I'm going to put it into joules as well. That gave me negative 165 joules per mole. Okay. Oh, and I did put it in joules. Okay, good. So now I'm going to extend this question just a little bit. What would the delta S of the surroundings be at 100 degrees Celsius? All right. So again, that energy is going somewhere, right? That heat is being released out into the surroundings. So I can take that 1.5 moles times negative 38.56, take the negative of that, so the opposite sign, that's what's being released out into the surroundings. Okay, so that would be 1.5 moles times 38.56. And then now in the bottom, I'm going to have 100 plus 273. And that tells me that if it were at 100 degrees Celsius, my delta S of the surroundings is 155.1 joules per Kelvin. And then I'd say, okay, well, but that would mean that my delta S of the universe is 9.5. And then that tells me, hey, that's a negative number. I know that a delta S of the universe, when it's negative, means that the process is non-spontaneous. This will not happen at 100 degrees Celsius. And that should make sense. If it were 100 degrees Celsius, I've made it so hot that my gas does not want to condense. It will not condense spontaneously, right? So I would get a positive value for delta S of the universe as soon as my surroundings were under that 78.3 degrees Celsius. And then that tells you, oh, it will spontaneously condense because now it's cold enough to do so. All right, so one word of advice when you are looking at questions on my practice questions, or if we're, in a couple weeks' time, if you're on the exam, make sure you are paying attention to delta S. Am I asking for the system, for the surroundings, or is it for the universe? Make sure you are getting the right, you're giving us the thing that we're looking for. Okay, yeah. Well, so the surroundings are at, I've increased the temperature to 100 degrees Celsius. My vapor, I had already brought, like the vapor itself is at 78.3 degrees Celsius. So like that would be like our ice block sitting out here. and that ice block is at 273. So I've already like done something funky with my preparation. Does that make sense? Kind of. So like in the real world, I see where your problem is. I think it makes more sense to be like, okay, block of ice sitting out here, the block of ice is still 273, or I've raised it up to that point. My vapor, I have prepared it so that my vapor is at 78.3 degrees Celsius and the surroundings are at 100 degrees. So maybe if I were going to like come up with a real world situation for this, I'm holding the room at, I have my ethanol, it was a vapor, I bring it down to 78.3 degrees Celsius, and then all of a sudden I turn the temperature up of the room around it. And then I ask myself, is it going to condense spontaneously? That, I know that this like doesn't sound like anything any normal person would do, but that would be the closest, like, if I had to set this up, that would be how I'd set it up. Okay, so that's a good question. Like when we are thinking about our phase changes, we're thinking about like our thing, our system, whatever we're at. A lot of times we're going to make this assumption that it's already at that temperature where it would change between one or the other. So I think the system that makes the most sense is the ice sitting out on the table. We know that that's at 273. We're wondering what happens when we go on either side of that temperature for the surroundings. All right. So that was like the big chunk of introductory work for entropy. And now we are going to go a little bit more in depth into entropy as a microscopic concept. And I really like this section. I like this section a lot more than what we just did. Okay? So we're going to think about it from, like, we are now going to shrink down and walk around amongst a system. Okay? And we're going to entropy to the molecular level. Okay? And this is going to, I think, help us have a more intuitive understanding of what entropy is, which is nice. Okay, so we're going to explore this system again. I've got two gases. I pull the partition, and they spread around. Okay, we're going to make a little tweak to it. We're going to look at two vessels. They are separated by a stopcock. On one side, I have vacuum. On the other side, I have two molecules. Okay, I open the stopcock, and I wonder how many configurations are there. We can do this. This is like if anybody has ever done combinatorics, like in math class, or like, you know, nope, that doesn't feel like that's landing, never mind. We're just going to look at how many different ways can I put these molecules on either side. They could be left and right, or swap left and right, both on either side, both on the right side. There are 4 configurations. I'm going to start using a word for configuration called microstate. There are 4 microstates. Okay? I can calculate the number of configurations here. I have 2 positions, and I have 2 particles. That means I have 4 configurations. So this is the number of positions. This is the number of particles. This gives me the number of configurations. All right, this is a nice hypothetical because I can actually visualize and think about 2 particles, right? But when we actually do this, if you were to fill one of these vessels, it would be a lot more. So we're going to slowly increase to more particles. We're going to do it again with 3 atoms, okay? I'm going to put 3 atoms on one side and then open the stopcock, okay? So now I have 2 positions with 3 particles. I'm going to have 8 microstates, okay? And now I ask myself, what's the likelihood? What's the likelihood of all of them being on the left side? Essentially, what's the probability that they self-compress? Okay, you all already knew, you pull the partition out, those molecules mix around. They don't come back to one side. So here we see that there's only 1 of 8. Okay, 1 of 8 configurations. Okay, that's 0.125, or like 12.5%, that all of them would be on the left side. But again, we don't usually work with 3 atoms. We usually work with maybe a mole. So what does that look like? Now I'm going to put a whole mole into my system. This side is a vacuum, and here's a mole of gas. Okay, again, I'm thinking about this simply. Are you on the left or the right side? When I stopcock, I have now 2 to Avogadro's number configurations. My calculator gives a glitch when I do this. It overflows. This is an insanely large number. There are so many different ways of positioning your particles just in 2 different places. So this is essentially, essentially an infinite, it's huge, okay? Which means that the likelihood that all of those particles would decide to be on one side, or that we would ever come to that microstate where all of them are on one side versus the other, is 0. We will never see that happen. Not because that microstate doesn't exist, it's just probabilistically, we're never going to encounter that 1 over infinity. So this is the probability of finding all particles on one side. Okay, so what's nice about this is we can connect this sort of probabilistic statistical approach to the macroscopic observation. We know we're never going to find all of those particles on one side or the other just when it's sitting there. And that checks out with this 1 over infinity. Okay, this area of chemistry is called statistical mechanics. All right. So this is nice. I love this conclusion. It's like, yeah, of course we would never find this. That is a really unlikely position to find. All right, so that's the connection. We're connecting sort of the number of microstates from the microscopic world to these observed macroscopic behaviors. Okay, so we're thinking about what are the number of ways I could put those particles. How does that justify or explain why the particles never wind up on that other side, that observation. Okay, the math of StatMech is, or I guess statistical thermodynamics or statistical mechanics. StatMech is hard. Okay, so we will mostly think about this on a conceptual level. Okay, we're not gonna do a lot more than just some conceptual statements here. All right, so we're gonna do that on the next slide. Some conceptual work. All right, so I have 1 mole of gas. I'm keeping it at some temperature T and a certain volume. Okay, if I want to know the number of microstates, okay, if I cannot capture each microstate. Okay, 1 mole, 6.022 times 10 to the 23. To describe all of those microstates, I would need all of the coordinates, and I would need all of their velocities. So how fast are they moving and in what direction? That's an insane amount. That's too much information to describe each one of those possible configurations. So instead of describing each configuration, we're just going to talk about the total number of microstates. Okay, so 2 slides or 3 slides ago or whatever, where it was okay, I can draw where those 3 atoms are. Okay, are they on the left or right side? That's doable, right? But now we can't do that. So we are just going to talk about the number of microstates, which we use capital W for. So number of microstates is W. Okay, capital W. And there is a direct connection. So Boltzmann, this guy, famously made the connection between the number of microstates, so W, and entropy, which is, remember, what we set out to do, is how are we going to explain entropy. Okay, so he said that S entropy equals K, which is Boltzmann's constant, times the natural log of W. So what we get out of this statement, okay, so this is a number. If you need this number, which we I don't think we ever ask you quantitative questions using this. The more important thing to see is that if W increases, entropy increases. If you have more configurations, if you can put your particles out in more space or give them more energy, that means entropy is increasing. That is the important connection. So this is kind of, I think, the more like pop culture-y way of talking about entropy is that the universe tends towards disorder. Okay, and this is where you see that connection. As entropy increases, we have more configurations. Okay, and that we often associate with disorder. Okay, more ways of spreading things out. Okay, more ways of dispersing energy. So most of the time, we're not going to ask you about the absolute value of entropy for a system. We're going to ask you about the change in entropy for a system. So let's write out, and now we can relate that back to the number of microstates. So if delta S of the system, which is a state function, is S, the final number of, or I guess the final entropy of the system, minus the final entropy, just like stop talking at this point, the initial entropy of the system, that would be K times the natural log of the configurations, the number of microstates in our final conditions, minus K times the natural log of the number of microstates at the initial conditions. And then we say, okay, we can condense that. We have some log rules. All right? And now I can say, I know if my change in entropy for the system is going to be positive or negative based on the number of microstates that I have at the beginning and at the end. So if I have more microstates at the end, which you could associate in your mind with more disorder, that would mean that delta S of the system is positive. Okay? We've increased the disorder of the system. We've provided more ways to put these particles in different places or different energies. That is an increase in entropy. If I had decreased it, if my microstates, if my final microstates are less than my initial microstates, that sounds like I'm confining them, or maybe I'm organizing them, or something that would constrain them. That would change in entropy that's negative. Okay? So we are going to, the next goal for us, for this class, is we want to make some sort of conceptually broad statements about what changes have an impact on our microstates, our number of configurations. Okay? This is the next class of question that you'll get on your exam. Okay? So I want you to, we have 5 minutes left. I want you to look at these two and think about how changing the volume and changing the temperature would change the number of microstates. So chat with the people next to you for 2 minutes, and then we'll come back together, and this will be our last slide for today. Okay. For simplicity, I have just represented my 1 mole with one single atom, and I have put it into this small box, or I have put it into this larger box. I have increased the volume. The number of microstates, okay, are the number of ways I could, like the number of positions and velocities that is available to all of my particles. In this smaller space, there are physically fewer places for those molecules to be, right? There's just less space. So there are fewer, literally thinking about, okay, I have to catalog like where each one of those particles is, its XYZ position. When I expand that space, there are more positions possible. So there are my W final is bigger. There are lots more ways. Okay, it'd be like if I have, if we were only sitting in the lower bowl of this class, okay, that's fewer potential spots for you to sit, right? So if it was just me, let's say there's like 100 seats down here. There's 100 different configurations. My W would be 100. But if I open the top, now there's 150 spots for me to sit. So now my W would be 150. Okay, there's just more ways of putting me in different spots when you increase the volume. The same holds true here. Because W final is bigger, this is my initial, an expansion, an increase in volume is always going to have an increase in entropy for the system. Okay, you give it more positions, there are more configurations, that means more entropy. The change in entropy is positive. Okay? The last piece here that we'll talk about is for temperature. And the thing to remember is that temperature is telling us about this distribution of energy for our particles. As I heat up, okay, this is colder, our blue is colder, red is hotter, I have more available kinetic energies. Remember I said that when we look at these configurations, I have to track their position and their velocity. This means that there are more possible velocities. So an increase in temperature also is going to be associated with an increase in entropy for my system. Okay? So there are more kinetic energies available. So an increase in temperature increases the number of configurations, so delta S would be positive. We will leave it there today and pick up with the rest of chapter 19 on Thursday.